Hi, this is my presentation on Lab 1, Constant Velocity, where we analyze an object in motion and create a model for it. Here is the video of our object. First off, we want to discuss some of the fundamental physics principles that underlie the idea of an object at a constant velocity, particularly Newton's two laws of motion. The first one states an object at rest remains at rest, and for our experiment, an object in motion remains in motion at constant speed unless acted on by an unbalanced force. Now, because our model represents constant velocity, this means that in our model, the net force must be zero. This relates to Newton's second law of motion, which states that force equals mass times acceleration. And since we're at constant velocity in our model, this means that our acceleration is zero, which makes our net force also zero. I'd also like to discuss a kinematic equation that we will be using, especially in our CloseScript program, which states that the velocity at a certain time is equal to the initial velocity added to the acceleration multiplied by the time. In this Sheets file, we have our data from our observed and our model. The blue line represents our tracking data, and the red line represents our model data. To create our model, we took the velocity at every single timestamp by doing the change in position over the change in time. And then to create the velocity for our model, we average every single velocity at the timestamp to plug in to our model. And this is represented in red. The model predicts the observed data pretty well. As you can see here, we calculated the average percent error at every timestamp, and it was 28.2. So in our CloseScript program, we have our initial conditions, which is our initial position, which we created to be zero, although in Tracker it's a little bit less than that. Our initial velocity is the same average value we took from all the velocity vectors at every timestamp. Our calculation loop ends at 2.835 seconds, which was the length of time that the object moved. Our net force is zero, as you can recall, due to Newton's laws of motion, because the model is at constant velocity. We use the same kinematic equation we discussed earlier, which is the velocity is equal to the initial velocity added to acceleration times time. This is acceleration written in the form of Newton's second law, and because the net force is zero, this entire term will equate to zero, and the velocity just equals the constant velocity, the initial velocity we set up here. And we simply create position to equal speed times time. To discuss some further questions in our experiment, if we flipped the axes from a positive to a negative, our velocity vector would become negative because our position graph would be sloping downwards instead of upwards. It is hard to tell how many pushes and pulls would allow our observed data to have a net force of zero, because this is not really like a textbook physics problem. It's in the real world, and there are a lot of forces at play that we can't specify. Thank you.